All right, let us get started on continuous functions. And continuous models are really the bread and butter of logarithms and natural logs. They're extremely fascinating, and you can use them in all kinds of sorts of problems. Again, temperature problems, decomposition, all kinds of scenarios, and one maybe we'll go over in the next video that are so helpful to be able to use. All right, well, let's just write one of our equations we had before. Y is equal to AE to the RT. All right. In this case right here, if you remember, A is my initial value, right? My starting value or my initial value. R is my percent rate, and T represents time, right? And because it's continuous, that tells me I'm using my the e to the x model, right? It's not compound or simple, it's continuous. And in class we learned how to be able to prove how we proved that we got to this equation here. All right, here it is. So let us get started. Well, we just kind of plug and chug. First of all, let's get our rate. Our rate is 7%. All right, and so we need to convert that to a decimal, so we just divide by 100%. It's kind of like the percentages kind of cancel out, and we're left with 0.07. Okay, and now that we have that, we just write our equation. Y is equal to, my starting value is 200 million e to the 0.07 times t, right? And that's literally it, my equation. I don't have to do anything fancy. I just got to divide the rate and plug it in. So how long until it has 300 colonies? Well, that's going to represent my y value. So 300 is equal to 200 e to the 0.07 t. And now we just continue. We divide both sides by 200. 300 divided by 200 is 1.5 is equal to e to the 0.07 times t. Well, to solve this problem here, we can take ln of both sides, right? Cancel out these, or we, like we have been. Let's convert this to its natural log form, right? Its natural log form or its inverse form. Well, we know e is so special, got its own inverse function. Ln is equal to blank. Well, if this is your output, that's now going to become your input, and if this is your input, that becomes your output. 0.07 times t. Now, to solve this problem, so let me just write it one more time. We have ln natural log of 1.5 is equal to 0.07 times t. Well, let's divide 0.07 on both sides, and we get t is equal to ln of 1.5 divided by 0.07. Let's grab this calculator and let's just go ahead and do that. Ln of 1.5 divided by 0.07, and we get 5.9 minutes. That means in 5.9 minutes, okay, in 5.9 minutes, we're going to grow from 200 million to 300 million colonies of bacteria on a rotten apple. All right, pretty crazy, pretty intense when you actually think about it for a second, that when you're dealing with bacteria, it grows tremendously fast. All right, let's just go ahead and take a look at maybe another example problem. Let's say we have another scenario. Let's say we have bacteria, okay, that grows. Let's start it off. Let's say bacteria with initial population of 128 million colonies. Okay, after 4 minutes, it has 200 million colonies. Okay, well, let's find the equation. Determine the equation. Okay, and how long will it take? We'll answer that question. Well, I'll write the question down in a minute, but how long will it take until it has 500? Well, let's begin writing our equation. All right, we got y is equal to, well, the initial population is 128 e to the, I don't know my percent rate. Doesn't tell me how much it's growing by. Well, that's okay, because look, it does tell me that after 4 minutes, it has 200 million colonies, right? It tells me that when t is equal to 4, the y value is 200. Let's plug that into my equation and let's solve for our rate of change, right? Because we do want to find out how long it will take until it has 400 million. So let's plug in 200. That's the y value is equal to 128 e to the r times 4. And let's use its natural log to solve for r. Well, first of all, let's divide 128 to both sides. And we're going to get 200 divided by 128. So let's write that down. 200, okay, divided by 128. And we get 1.5625. So 1.5625 is equal to e to the, well, instead of writing r times 4, let me just write it as 4 times r. We usually like to have the number in front. Again, it doesn't matter whether you do 2 times 3 or 3 times 2. You're still going to get 6. So r times 4 is the same thing as 4 times r. Now, to convert this to logarithmic form, well, because it's e continuous, it gets its own special inverse. And we get, this is the output, so that becomes the input, 1.5625, and this is the input, so that becomes the output. Okay, so let's go ahead and write that down real quick here. We got ln of 1.5625 is equal to 4r. Well, what do we do to get rid of the 4? Well, we just divide 4 to both sides, and we're going to get that r is equal to, let's go ahead and do ln of 1.5625 divided by 4, and we get 0.11157. Okay, 0.1157 is my rate. Now that I have my rate, let's go ahead and plug that into my equation. So we now have y is equal to 128, which was my starting amount, is e to the, well, now we know this is 0.1157 times t. Okay, we figured out our rate of change. Now we can ask the question, right? This is what we wanted to get at. How long until we have 400 colonies? Okay, well, let's plug the 400 in for the y, and we get 128 e to the 0.1157 times t. And look, it's almost the same process. We want to find how long. Well, that's what t represents. So what do? We divide 128 to both sides, and we do 400 divided by 128. Let's see, 400. Oh, it's 0.11157. Whoo, good catch there. Let's write that, 0.1157. Okay, if you didn't catch it, let's go back up here and make sure we adjust this. 0.1157, 0.1157. That could have made a significant difference, all right? And if we pull that up again, let me see. Oh yeah, 400 divided by 128, which is 3.125, which is equal to e to the 0.11157 times t. Now to convert this to natural log form, it's got its own special inverse. So ln natural log blank is equal to blank. All right, this is your output, so that becomes your input, 3.125. This is your input, so that becomes your output, 0.11157 times t. Let me just write that one more time. Ln of 3.125 is equal to 0.11157 times t. Well, what do you do to get rid of this? Well, we divide it out. 0.11157. Divide this to both sides. 0.11157. And we get t is equal to ln of 3.125 divided by 0.11157. and 10.21 minutes. So in 10.21 minutes, it's going to grow to 400 colonies, right? And this problem was kind of cool because in this problem, I didn't give you the rate, but I did give you a key piece of information, which is I gave you basically that when there's 4 minutes passes by, it's going to be at 200 colonies, and we could plug that in to solve for R. Then we plug R back in, and then we can plug in the 400 and then begin to solve. Pretty darn cool if you ask me. All right, you take it easy. Hopefully this collection of videos for our logarithm functions have helped you to better understand what a logarithm is, which is an inverse of an exponential function, and how to convert and solve and why they are so freaking useful. Thank you.